So we are going to proceed with Peter Nicholas. Hello. Okay.
Hello there.
Yes, I can hear you now. So Peter is going to present o8t labs, an automated machine learning based approach to personalized brain mapping and functional connectomics.
It is a bit of a mouthful, isn't it?
Yeah.
Would you be able to confirm that my screen is coming through okay?
Yes, it's coming through okay.
Awesome. I can launch into it now if you'd like.
What, sorry?
I can get started now if you'd like.
Yeah. Go ahead.
Okay. Good morning, everyone, and thank you for your time. Thanks for the introduction. My name is Peter Nicholas, and I'm a senior data scientist at Omniscient Neurotechnology, or o8t. I think it'll be a bit easier for people to remember and say that. Today, I'm going to be presenting on our workflow, actually, and that is a automated machine learning-based approach to personalized brain mapping and functional connectomics. And broadly, what this aims to do is generate functional connectomics in a kind of easy, seamless way and enable researchers to spend more time researching. So to begin with, a brief introduction to functional connectomics. I'm very glad that I get to follow up Stuart because there's a lot of overlap with the structural connectomics that he just mentioned. We begin with a brain parcellation. And then for each of those parcellations, we're kind of extracting out the resting state fMRI signal. We're looking at the correlation between each of those signals, and we're kind of constructing an adjacency matrix or a functional connectome that I've heard quite a useful analogy. It's how the cities and highways of the brain kind of fire together. So basically what we're producing here is a map of what areas fire together, and we're using bold signal change to quantify and generate that map. Why is this valuable? Well, functional connectomics have enormous potential. They offer kind of unparalleled insight into brain disease because it enables you to kind of trace brain activity to functional patterns. Once you start putting a label on these functional connectomics, Alzheimer's, depression, what have you, you can start doing some really interesting analysis. And it starts giving you an opportunity to leverage big data. It's much easier to work with 1,000 functional connectomes than it is 1,000 resting state MRI scans. Unfortunately, this does come with some barriers to entry. As we might all know, it's quite a time-demanding workflow, not easily scalable, unfortunately. And there's a lot of expertise required in the pre-processing. That is to say, just general data cleaning and processing. It's not the kind of sexy stuff, it's not the elegant stuff, but it is incredibly important. And with this comes a lack of standardization. The necessary variance in all these pre-processing pipelines does raise some concerns for replicability and kind of lack of standardization across studies. So how have we approached this kind of problem? Well, the first thing I'd like to mention is the personalized atlasing approach. So this starts with a diffusion MRI scan and involves the generation of CST tractography, as you can see in the middle diagram on the bottom row. We use this CST tractography to update the standard atlas and generate a machine learning adjusted atlas, which is what we're seeing in the middle diagram on the top row. Then the combination of that parcellation scheme with resting state fMRI enables us to generate structural and functional adjacency matrices, or connectomes rather, that are more accurate than a traditional kind of 3D registration of atlas. We do a lot of work with people with tumors and cavities who have had tumors resected. And so this methodology allows us to kind of work with deformities like that. The other part of making this workflow automated and effortless is in achieving kind of computational scale. So a lot of the pre-processing steps are quite complicated and time-consuming. And what we do to obfuscate and abstract that away is what I've just highlighted in red to the right. Send that all off to the cloud for processing. So we kind of run all this processing in parallel in the cloud, and that enables us to kind of launch many, many jobs in parallel and not have to iterate through all of them sequentially, as I've seen people do on their local laptop, and that is just the biggest headache. We actually happen to do a lot of work with clinical researchers. So as a necessity, we've kind of built in, an interface to typical hospital infrastructure and the ability to work with DICOMs. A lot of the concern they have, rightly so, is in patient security, patient data sensitivity, and matters like that. So because of that, things like de-identifying the data, stripping DICOM headers, etc., face removal, all of these are very much desired by those kind of researchers who want to take data concerns very seriously. And then I'll just mention it, but not so relevant for the researchers, but for actual clinicians that want to use this data, once we've de-anonymized it and they want to use it in the clinical practice, we can actually reattach the face, reattach those data points that we've stripped away for privacy. So at this point, I'm just going to kind of give a quick demonstration of the workflow itself, not a demonstration of research and results. This is very much kind of work in progress, but I thought I'd just kind of ground this in reality and, put some kind of context around this workflow, which I'm espousing. So recently we worked with a group in China who wanted to use our workflow to generate functional connectomics on a set of schizophrenia subjects that they had. They came to us with a very, I'd say, ambitious turnaround time, requesting that we generate the data for 125 schizophrenic subjects before and after treatment, as well as 100 matched controls. Concretely, what this meant was that there were 250 fMRI cases that we needed to process, as well as all the CST tractography, motion realignment, all of that happens in the background. And by launching these in parallel in a swarm, up in the cloud in our automated workflow, it was a less than 24 hours runtime until we could get the results back to that team and they could start doing the research that they wanted to spend their time on, kind of saving them the time to fiddle around with different pre-processing pipelines and trying to link together the computing power to get the job done. So I've been talking about this workflow so far, but I'd just like to touch on where it might be going in the future. So unfortunately, some of this slide is already outdated. I have on the left here structural and functional fingerprint of Alzheimer's as an area of research. We've already been working with some teams to get started on that. And what that looks like is very similar to what I previously outlined, but kind of enabling our workflow on someone else's data to get them the data that they require to start looking at what kind of functional connectomes and structural connectomes are unique to Alzheimer's. There's also a large undertaking in quantifying the impact of brain surgery. As I mentioned before, we do a lot of work with clinicians that have patients with tumors and want to see what the impact of resecting those tumors are. And it would be incredibly insightful to put a number on the impact of a brain surgery and empower the surgeon and the patient that way. And an ongoing research area that we're looking to get into is into responsiveness to treatment in depression. Excuse me, depression. But in the long term, this is going to necessitate some upgrades to the workflow itself. So a big area of focus is in multi-source data homogeneity. And what I mean by that is that if you want to leverage big data, you need a lot of it, and it's going to, out of necessity, be collected across multiple sites, different scanners, different protocols. You cannot just use that willy-nilly. You need to take some sort of standardization practices into account to make that comparison fair and valid across multiple sites. We're going to be extending our analytical use cases. So right now I've shown you really only functional connectomics and a little bit of structural connectomics, but there's so many other things that would be good to automate into our online workflow. There's some machine learning smarts behind all of this, and it is, as you'd want to see, it's good to iterate that and continually improve and improve that over time. And then in the medium to long term, a kind of goal is to shorten the bridge from academia to clinical practice and bring some of the great ideas into the hands of clinicians as soon as possible. So before I run out of time, and so that I don't get yelled at by the people upstairs, I will quickly touch on exactly what I've been talking about this whole time, the offering in question, and that is o8t Labs. It's a fairly available and unlimited tier offering for generating these structural and functional connectomics. It lets you investigate at the subject level. I mean, the user on the right is navigating the viewer, and that's completely in Google Chrome. So, no software needed to install, can work on anyone's laptop. And the use case here is to help people organize their huge data sets, identify particular patients of interest, and export kind of academic research insights as they desire, things like connectomes, but very much use it how you desire. So with that, I'll open to questions. Thank you for letting me present, and yeah, it's been an honor to present here.
Thank you very much, Peter. It was a wonderful presentation. We have one question already in the Q&A chat, and I'll read that for you. So John asks, I noticed your parcellation of cortex derives from one economo and not Brodmann. What was the reason?
Yeah, that's a really good pickup, given how quickly I blasted through all those slides. So we actually went with the HCP MMP Atlas that came out of the Glasser research study. We felt like at the time that was, I guess, kind of the cutting edge, and so we just went with it. There is definite need to kind of evaluate the whole world of parcellation schemas, and I think a lot of them actually, I don't even think that there's a one size fits all or there's a best. I think different schemas offer different advantages and disadvantages. So in response to your question, we happened to go with HCP MMP because it was detailed, granular, which is exactly what we wanted at the time. But I'm sure there's a lot of value in the other schemas that you've outlined and the ones that are out there. I noticed now that he's linked to forbrain.org.
Yeah.
That's something I'll check out.
Yeah, thank you. And I also have a follow-up question, which is, so you mentioned you want to deploy this, especially for clinicians or for researchers in the area. And I was wondering, if you also had a plan for making task fMRI and the task connectomics supported by your platform, especially considering the variability that there is there whenever you design a task and you design an fMRI study, and how you plan to cope with that.
That's a really fascinating question. We're in an interesting space where we work with researchers and clinicians, and we've actually found that clinicians much prefer resting state because it's a bit more hands-off. But there's been enormous interest in having something similar for task-based, where you can see the impact of a stimuli. a lot of clinicians have expressed an interest in kind of being able to do a task-based fMRI, but without the task. So that is to say, seeing where vision would fire if you were to do a vision task, or where motor system would fire if you were to do a motor system task, but getting as much of that as possible out of a resting state scan. And that's, you know, that's not a small question. Would be a dream, honestly. But yeah, so there's been a lot of demand there, and something we need to look into.
Yeah, no, sorry for the difficult question. I know it was like much broader than the time that we have available.
No, it's a good question.
But yeah, I was curious about like your take on that. We also have a kind of sort of a question, if you can share your contact information in the chat. It was like, I don't know if you can, I think you can see the chat. Larissa was asking if you have like a interest in connecting with her for discussing the o8t program further.
Oh, absolutely. Yeah, thank you for your interest. I'll share the details in the chat, and yeah, reach out.
Yeah. So I'm just waiting for another maybe 1 minute or so if anyone has any other question for Peter. In the meantime, I wanted to ask you, like, what are your plans from the machine learning perspective? Like, if you're planning to implement some algorithms in your framework, or just leverage on other platforms for machine learning?
That's a great question. I think there are so much great work out there that we should definitely leverage as much as possible. Specifically, a lot of the programs we have on the back burner are machine learning analysis of functional and structural connectomics, and people have had enormous success in that. It's astounding what they've been able to achieve. As I touched on, a huge concern for us is multi-site, multi-scanner kind of site-specific issues and those kind of confounds. So I think that's the big challenge to get over first. We'd want to have some assurance that whatever machine learning we're applying to our connectomics or whatever it may be will work across the board as much as possible. But yeah, there's a lot of great research out there.
Thank you very much. So with that, I think we have no further questions. Let's thank Peter again for his presentation, and also Stuart, our previous speaker.